So, right, okay, guys, we are going to discuss the calorimetry tutorial, the rest of the calorimetry tutorial, right? So, actually, so this is going to be the calorimetry tutorial session 3, I guess, right? So, I have already posted 2 sessions in calorimetry. So, this is going to be the calorimetry tutorial session 2, right? So, here we are going to mainly focus on the state transition section in the calorimetry part, right? So, state transition. Okay, fine. Let us see the 20th question, right? So it says a calorimeter of heat capacity 96 joules per Kelvin contains 0.2 kilograms of solid paraffin, right? It contains 0.2 kilogram of solid paraffin at room temperature 24 degrees Celsius. The room temperature is 24 degrees Celsius. The calorimeter is well lagged, so therefore no heat loss takes place. The specific heat capacity of paraffin is 20 joules per per Kelvin. The system is provided with heat at a constant rate 100 joules per second. The first question A, it says if it takes 160 seconds to melt paraffin completely, find the melting point of paraffin. So it should be slightly corrected as if it takes 160 seconds for the paraffin to reach the melting point, right? To paraffin to reach melting point, then find the melting point of the paraffin. Right? Okay, fine. So this is the 20th question. So what it says is there's a certain calorimeter. In that calorimeter, there's a certain amount of paraffin, 0.2 kilogram of paraffin, right? So this paraffin specific this thing what you call the heat capacity is 2020, right? Joules per kilogram per degree Celsius, right? And the specific heat capacity of the calorimeter is 90, not the specific heat capacity, the heat capacity of the calorimeter is 96 joules per kilogram, uh, joules per kilogram per degree Celsius, right? So not per kilogram, sorry, okay, so it's heat capacity. Okay, fine. So, right, fine. Now what else? Initially, all these are at the room temperature, they're saying. The room temperature is 24 degrees Celsius. We need to find. So what they're saying is by means of a certain manner, they are constantly supplying heat at a rate of what? They supply heat at a rate of 100 joules per second. They're constantly supplying heat at a rate of 100 joules per second. So this heat supplied, this constant rate of heat supplied, so when this heat is applied, what's going to happen? Actually, the calorimeter is going to absorb heat, right? The calorimeter is going to absorb heat as well as apart from the calorimeter, the paraffin also is going to absorb heat, right? So the heat supplied is going to be absorbed by the calorimeter plus the paraffin, right? So heat supplied equals to heat absorbed by calorimeter plus paraffin, right? Paraffin. So these are the two people who are going to absorb the heat that is applied in this kind of a way, right? So how, like, okay, so in order to reach, like, it takes around 160 seconds, for the paraffin to reach its melting point, right? It takes 160 seconds for the paraffin to reach its melting point. So therefore, heat is supplied for how long? 100 into how long? 160 seconds. Joules per second into seconds. Second per second into second cancels out, right? So this is joules. So this amount of heat is supplied, right? So supplying 100 joules per second uh, for 160 seconds. If you multiply, it's going to give you how much heat was supplied within this 160 seconds, right? Okay, this amount of heat was supplied. So that amount of heat was absorbed by whom? by the calorimeter and paraffin. So specific heat capacity of paraffin is given. Let us assume, okay, so since both the paraffin and the calorimeter are in thermal contact, they should both reach the same temperature. So theta m minus, it was initially at 24 degrees Celsius, right? Okay. So what's the mass of the calorimeter? Mass of the paraffin 0.2, right? Its specific heat capacity is 20. So it increases its temperature from 24 to this melting point, right? So 24, sorry, theta m minus 24. So if you simplify this guy, you are going to get theta m to be as 56 degrees, right? So this is going to be the answer, 56 degrees. Right. Okay. So in the next B part, they're saying after that temperature of paraffin, right? After that, after paraffin reaches its melting point, what happens is its temperature remains unchanged for 7 minutes. You know, right? So like after a certain substance reaches its melting point, it's going to uh, like it's not going to vary anymore. I mean, like the temperature, although you continuously supply a heat, the temperature will not vary for a certain while. What is that state? It is the state transition state, right? So the phase changes from solid to liquid at this moment, right? So it had taken 7 minutes for the paraffin to completely convert into this thing, what you call uh, yeah, 7 minutes, right? 7 minutes to completely convert into liquid. So it's like this. So to the paraffin, right? To the paraffin, you keep on supplying this thing, what you call the heat at this rate. After it reaches its melting point, for example, now this is in its melting point, right? You need to make sure, right? Okay, this calorimeter is in its melting point. The paraffin is in now in its melting point 56 degrees Celsius, right? So now you but keep on supplying heat, but the temperature will not vary. Why? Because this is a state transition situation, right? So for how long the temperature will remain constant? For 7 minutes, right? For 7 minutes means 760 seconds, right? Okay, fine. Now when you keep on supplying this, what happens? Actually, here also heat supplied 100 into for how long heat was supplied? This amount of time. So 100 joules into this amount of joules per second into this amount of seconds. Heat was supplied. This supplied heat was absorbed by whom exactly? It was absorbed by the so when heat is supplied, right? That heat, like at this moment, since there's no temperature change, the calorimeter is not going to absorb heat, right? So like since there's no temperature change, the calorimeter is not going to absorb any heat. So the complete heat supplied is going to be used by the paraffin to change its state. So how do we write it exactly? State changes m into L, right? M into L. So actually we know what M is. We know what M is. Okay, 100 into 7 into 60 is equal to M is 0.2 kilograms divided by into L, right? So in that case, L is going to be given as something closer to 2.1 into 10 to the power 5, I guess, right? 2.1 into 10 to the power 5 joules per kilogram, right? Per kilogram. This is going to be the fusion, right? This is going to be the latent heat of fusion, right? Okay, right. So in the C part, what it says is, right? In the C part, they're saying that the temperature reached to a steady 84 degrees Celsius, another 14 in another 14 minutes. Determine the specific heat capacity of the liquid paraffin. Now, what happens after these 7 minutes, right? So, like the liquid, like the solid completely converts into liquid, right? Solid completely converts into liquid. Now there is liquid in this calorimeter. Now what's there is liquid paraffin, right? Liquid paraffin which is in 54 degrees Celsius. Liquid paraffin in 54 degrees Celsius. Initially it was solid paraffin which was at 54 degrees Celsius. Now it is liquid paraffin which is at 54 degrees Celsius, right? So now to this constantly heat is applied at a rate of what? The same old rate, 100 joules per second. So when this heat is supplied at this rate for another 14 minutes, right? 14 minutes means 40 into 60 seconds. If when it was supplied to this amount of a time, the temperature of this reached to a steady of what exactly? Did reach to 84, right? It reached to 84 degrees Celsius, right? So now this is in liquid state, right? Now it's in liquid state. So now of course the heat supplied by the heat supplied is going to be absorbed by both the calorimeter plus the paraffin, right? So heat supplied is what? Now 100 into 14 into 60, right? This amount of heat was supplied for 40 minutes. This amount of heat was applied, that was absorbed by whom exactly? By the paraffin, liquid paraffin, m into, so liquid paraffin mass is given, right? Mass was given 0.2, right? 0.2 into the specific heat capacity of liquid paraffin is not known. For us, what was given was the specific heat capacity of the solid paraffin. So when it converts into liquid, its specific heat capacity changes, guys, right? So you need to understand. Now we do not know the specific heat capacity of the liquid paraffin, right? Now, but what we know is, we know the temperature change. The temperature was changed from 84 to 54 plus, and the heat capacity of the calorimeter is still 96, right? So the temperature change is 84 minus 54, right? So heat supplied for 14 minutes was absorbed by the liquid paraffin plus the calorimeter, right? So if you simplify this, you are going to get the specific heat capacity of liquid paraffin to be as 1.5 into 10 to the power 4, right? 1.5 into 10 to the power 4 joules per kilogram per Kelvin, right? So this is going to be the liquid paraffin's specific heat capacity, right? Right now, guys, you need to understand the eight in the D part. What they're saying is, with the continuous heat supply, all the paraffin vaporized. Now in the C part, that you need to note this point, right? So then the temperature reached to a steady 84 degrees Celsius. So the liquid paraffin reached to its steady state, means like it has reached its boiling point. This is its boiling point, right? You need to note that is 84 is its boiling point. It's going to be steady, right? So if it is steady, then that is considered as the boiling point, right? So now the liquid is in its boiling point. So when it is in its boiling point, and when we continuously supply heat, right, continuously supply heat, all the paraffin vaporized, it converted into vapor within 24 minutes and 40 seconds, right? Find the latent heat of vaporization of paraffin. This is what you need to find, right? Okay, fine. Now what they're saying is, guys, so in the D part, there's liquid paraffin, right? Liquid paraffin in 84 degrees Celsius. This is its boiling point, right? So this is its boiling point. So further, when you supply heat, the temperature, will it increase? No, the temperature will not increase, because it's going to go into its transition state, right? It's going to go into its transition state. I mean, like, it's going to, now the liquid is going to convert into what? It's going to convert into gas at the same temperature, right? It's going to convert into gas, right, at the same temperature. Fine, let us do that. Now heat is supplied for 24 minutes, 24 into 60 seconds plus 40 minutes, right? Okay, so the heat supplied is constant, right? It is 100 joules per second. So exactly what is the amount of heat supplied within this amount of time? It is 100 into 24 into 60 plus 40 equals to, right, equals to, what is its mass? 0.2. The latent heat of fusion is capital L, right? So the heat that is supplied is completely going to be absorbed by the liquid to convert itself to its gaseous state. So that is the latent heat. So in this case, since there's no heat change, since there's no temperature change, the calorimeter will not absorb any amount of heat, right? So the complete heat supplied is going to be absorbed only by the liquid, right? So if you simplify this, you are going to get L to be as something around closer to 7.4 into 10 to the power 5, right? 7.4 into 10 to the power 5 kilo uh, joules per kilogram, joules per kilogram per degree Celsius, we can say, right? Sorry, not per degree Celsius, per kilogram, right? Per kilogram. So this is the latent heat of vaporization, right? And in the final E part, what they are saying is, in the E part, right? Sketch the variation of the temperature of the above system with time. We need to draw with time. Okay, temperature with time, right? Let us draw a figure, right? Just give me a sec. Right, so let us mark this as the temperature and time, right? So initially the solid paraffin was at to room temperature 24 degrees Celsius, right? So and then what happened? When we supplied heat, its temperature varied until 54 degrees Celsius was its melting point. At the melting point, when you further supply heat, its temperature remained constant for a certain amount of time, right? For a certain amount of time, it remained constant. And then what happens next is, after it, now at this moment, what has happened at the melting point, this was solid. The solid completely converted into liquid. Liquid now further increase its temperature to what? The liquid paraffin increased its temperature to something around 84 degrees Celsius, and then once again, the once it reaches its boiling point, the temperature did not change. It kept on going constant, and then after it will increase, right? So this is going to be the variation, right? So variation of the temperature versus time, right? So, all right, guys, let us discuss the 23rd question. Since some of you guys requested this, I'll discuss the 23rd one, right? So it says there is a body of mass 25 kilograms and it is dragged on a rough horizontal road for 1 hour. Very important, 1 hour, with a speed of 20 kilometers per hour. If the coefficient of friction is 0.5, if the coefficient of friction is 0.5, half of the heat produced is absorbed by the body. The rise in its temperature is the specific heat capacity of the body is given. So it's like this, guys, right? So this is the 23rd question. There is a certain body, right? So for example, there is a certain body and there is a rough flow or something, right? When this is dragged on this rough flow where the frictional coefficient is something around zero point 0.5, right? The frictional coefficient is 0.5. So when this is dragged on this, what happens? It's going to exert a frictional force, right? So it's going to exert a frictional force, simple F, and then there's going to be the weight acting downwards, mg, and also there's going to be the reactional force, right? So now how do we find this? Like it was with a speed 20, right? Okay, so the frictional force applied is applying due to this frictional force only, the heat is going to arise, because like when you drag something on a rough flow, like when the object does work on this when the object does work on this frictional force, uh, the energy is going to be wasted as heat, right? Energy is going to be wasted as in the form of heat, right? So how do we find the frictional force? It is simply mu into r. We can find it as mu into r, right? So right, okay, mu is 0.5, r is what exactly? R is equal to mg. Mg is what? 25 kilograms, which means this is 250 newtons, right? Isn't it? 2500 newtons. Sorry, 250 newtons, because the mass was 25, right? 250 newtons. So this is going to be 250 into 0.5 means it's going to be 125 newtons. The frictional force is 125 newtons. Now, okay, because of this frictional force only, a heat is going to be produced. So shall we find the rate of heat produced? We can find the rate of heat produced, or else it's power, right? So how can we find this power? That is F into V, F into V, right? So fine, F into V. So F is 125 newtons. What is V? It is moved with a speed which is equal to 20 kilometers per hour. 20 kilometers per hour. So I'm not going to convert this into, okay, 20 kilometers means 2000 meters per hour. Per hour, right? Per hour, 2000 meters per hour, right? So actually this was dragged for how long? This was dragged for 1 hour. This was dragged for 1 hour. Therefore, energy wasted or energy released, right? Energy wasted is how much? It's simply this into the, like, how do you find it? Power into time, right? Energy is found as power into time. So the rate of energy wasted is this. This was wasted for how long? 1 hour. So 125 into 2000 over 1 hour was wasted for 1 hour. So this cancels out, right? P into T. So this is given in joules. 125, right? 125 into 2000 is going to be 250,000 joules, right? So out of this energy wasted, out of this heat energy wasted, half of it was absorbed by the, exactly half of it was absorbed by the object. Half of it was absorbed by the object. So how much did the object absorb? Object absorbed half of it, exactly. How do you find half of it? 125,000 joules. This is divided by 2. So because of this heat energy absorbed by the object, its temperature is going to rise, delta T, mc delta T. So what they are asking is the increase in temperature. So okay, the energy absorbed by the object is 12500 joules. Mass is 25. The specific heat capacity of the object is 420 into delta T. So if you simplify this, right, divide by 25 divide by 420, you're going to get something around yeah, something closer to, let me check. Okay, fine. So there is a small error, that is like actually the speed of this was 220 kilometers per hour, which means it should be 20,000 meters per hour, right? So in all these answers there should be a zero in addition, right? So there should be a zero here in addition as well. So if you simplify now, of course, you are going to get delta theta as 119 degree Celsius, right? So this is the increase in temperature, and there is an answer, that is the fifth answer.